Aloha BIOCHEM. This video begins Chapter 5 on chemical reactions, and we'll introduce reactions, balance their equations, and classify them into different categories. So we're finally starting Chapter 5 on chemical reactions. I say finally because it's one of my favorite topics. You can see in the picture here several brands of the drug aspirin. Aspirin's an important pain reliever, and it's also used to prevent heart attacks or to treat active heart attacks. Now, aspirin is synthesized by drug companies from a naturally occurring substance. And in fact, if you go back to our very first lecture, where we divided matter into naturally occurring substances and synthetic substances, one of the examples was salicylic acid. And this is the precursor to aspirin. Salicylic acid is extracted from plant sources like white willow bark, taro, coffee, etc., and it's used as a skin treatment. But if you take this naturally occurring substance and you do a simple reaction on it, if you just react it with either acetic acid or acetic anhydride, then you generate the drug aspirin. And you can see the similarity in the two molecules here. Aspirin has this portion added onto it right there. Aspirin is also called acetyl salicylic acid. I'll show you another more detailed representation of the reaction here. So here's your naturally occurring salicylic acid, extracted from plant sources. If you react that with acetic acid, which you can get from vinegar, then you will generate aspirin or acetyl salicylic acid. And hopefully the color coding makes it clear which portion of the molecule comes from the acetic acid. Now the byproduct here is water, so you also get water. But here's your aspirin. So this chemical reaction is important in the pharmaceutical industry, and there are countless other chemical reactions that are taken advantage of by drug companies as well. And in this chapter, we will discuss reactions in pretty good detail. In this first video, we cover sections 5.1 through 5.3. In the next video, we get into oxidation and reduction. In the last 2 or 3 videos, we'll deal with the mathematics of chemical reactions. Here are the notes. Let's first compare chemical reactions, also known as chemical changes, with physical changes. We did this back in Chapter 1, so hopefully this looks a little familiar. A physical change alters a substance without changing its identity. An example is solid water changes into liquid water. The little triangle on top of the arrow is the Greek letter delta, and that represents heat. So solid water with a little bit of heat converts into liquid water. You should be aware of symbols like this. So table 5.1 shows you a few symbols you'll come across. So the Greek letter delta represents heat, and also, of course, the phases that you'll see. So solids, liquids, gases, and aqueous. But there are a few other symbols that you might see from time to time. And they're always written on top of the arrow if it helps the conversion takes place. Now, physical changes are also easily reversed. And it's pretty easy to convert liquid water back into solid water if you simply cool it down. Your author shows you a picture of this physical change. So here it is, an iceberg floating in the ocean. Maybe it's floating south towards the South Pacific. And along the way, it's getting smaller and smaller, and that's because it's melting. And so, you know, the water in the solid phase, all these water molecules are nicely lined up, you know, ordered structure. And then after it melts, the water molecules are all disordered. Physical changes have pretty simple chemical equations because the substance that you start with is the same as the substance that you end up with. The chemical formulas are the same. It's just the state has changed in this case. Another example of a physical change is solid sodium chloride, with the help of a little bit of water, dissolves into aqueous sodium chloride. So again, the chemical formula is the same on the left and on the right. And it's easily reversed as well here. If you simply evaporate the water or boil it off, you will be left with a solid residue again. Now, chemical changes are more involved. A chemical change converts substances into other substances. And an example is the combustion of propane, or the burning of propane. Here is the chemical equation for the combustion of propane. And you start with propane gas and oxygen gas, and if you react these together with the help of a spark, they will convert into carbon dioxide gas and water gas. The substances that you start with are called the reactant substances because they're reacting together, and those that you produce are called the products. And these little numbers in front of the chemical formulas are called coefficients. The reason you need coefficients is because they account for all of the atoms in the change. So here, the way you should read this is 1 molecule of propane gas reacts with 5 molecules of oxygen to produce 3 molecules of carbon dioxide and 4 molecules of water. That's how many molecules are involved in the chemical reaction. You see, 1 propane molecule needs 5 oxygen molecules in order to fully burn. So to maybe get a better view of what's going on here, the propane molecule, the oxygen molecule, the carbon dioxide and water molecules, when you see the reaction scaled properly, one of these propane molecules needs 5 oxygen molecules to fully react. Okay? And then when that happens, you get 3 carbon dioxides and 4 waters. So it's accounting for the atoms. If you just have 1 propane molecule, you cannot just generate 1 water molecule, because after all, where did the rest of the hydrogen atoms go? If the propane molecule converts, you start with 6 hydrogen atoms over here, but there are only 2 over there. And so, same thing with carbons. You got 3 carbons over here and you only have 1 over there. So, the coefficients are added because you're accounting for all of the atoms. Okay, so we'll get into balancing chemical equations here shortly. But that's what a chemical equation looks like for chemical changes. They're a little bit more involved, and you can identify this as a chemical change because, again, you have different substances, different chemical formulas on the left, the reactant side, versus the right. So you're generating new substances here. Another example of a chemical reaction is the metabolism of glucose. Now, interestingly, you generate the same products in the metabolism of glucose. Glucose is a type of carbohydrate that you get from lots of pastas and breads, as you can see right here in this image in your textbook. So pastas and breads and grainy material have carbohydrates, and you can get glucose. They have a lot of glucose in there as well, and your body needs glucose. Cells need it. So the way your body uses glucose is through the following chemical reaction. Glucose, when it's dissolved in the cell, is in the aqueous phase, and glucose reacts with oxygen gas. Okay, oxygen in the cell. And these 2 chemicals, with the help of certain enzymes, convert into carbon dioxide and water. So this chemical reaction is pretty complex, and in the body, it occurs in a sequence of steps. So many steps are involved, but at the end of the day, these chemicals, after a series of steps with the help of certain enzyme molecules, react to form carbon dioxide and water. And the carbon dioxide is exhaled. So that's how you get rid of your carbon. Okay, so you eat your foods which contain glucose, and through the metabolism of glucose, you will exhale carbon dioxide, and you get a little bit of water. Now, interestingly, this chemical reaction can be reversed. Okay, chemical reactions are not easily reversed. Okay, as opposed to physical changes, chemical changes are not easily reversed. Okay, but metabolism of glucose can be reversed actually with the help of plants. And what plants do is they take carbon dioxide in the air and water, which they receive from the rain, and they convert to form glucose and oxygen. So plants take air and water, and they convert that into glucose and oxygen. So plants produce oxygen. So it's interesting. We consume foods which contain glucose, and we metabolize that into carbon dioxide and water, and then plants kind of do the reverse process. So it's a nice little cycle. Plants do this with the help of light, and so that process is called photosynthesis. Okay. So the exact opposite of this reaction by plants. Let's take a look at a few examples of either chemical changes or physical changes. So remember, chemical changes, you have different substances on the left versus on the right. This is an example of a chemical reaction that occurs between methane, which is CH4, and oxygen. Okay, CH4 and oxygen. You have different molecules on the left, and after they burn together, you end up with carbon dioxide and water on the right over here. So chemical changes are pretty easily identified because the molecules that you start with are different than those that you end up with. Now this sample problem right here asks us to identify a chemical reaction, in a physical change. So which one of these is a chemical change and which one is a physical change? Let's start with the one on the left. Okay, so here you have these particles converting into those particles. So is this a chemical change or a physical change? It's a chemical change because you have different types of particles, different molecules on the left versus on the right. If you remember, the blue ones are nitrogens and the red ones are oxygens. So this is an N2 molecule and that's an O2 molecule. So you have nitrogen and oxygen converting to form NO. That's nitrogen monoxide. So that's a chemical change. What about B? Now this right here, you probably can recognize these as water molecules. You have a bunch of water molecules which are close together and they're disordered. So that looks like liquid water converting into water vapor. Okay, the molecules are far apart. So that's a physical change. It looks like evaporation or boiling to me. Let's see any more examples. Yeah, here's one right here. So is this a chemical change or physical change? This is a chemical change. Here you have these white ones, which are hydrogens, so H2 and O2. Okay, so you have hydrogen and oxygen, two separate substances here because you have two different types of particles, hydrogen and oxygen. Okay, and then they convert to form water. Okay, so chemical change. How about this one right here? So it looks like the particles are the same on the left and on the right. I'm not sure what these green ones represent. Maybe there's some metal atom. Maybe this is sodium metal or something. But it looks like these are all disordered and those are ordered. So this could be liquid sodium converts into solid sodium. So that would be a physical change. Okay. So an interesting few examples right there. Now, let's discuss balancing chemical equations. How do we know what numbers go in front of the chemical formulas in the balanced chemical equation? How do we get those numbers? Well, there's a pretty straightforward process. It's not difficult to do. And let's illustrate it with the combustion of methane. So we just saw this one a second ago in one of those pictures. Methane gas is CH4, and it's kind of like the combustion of propane. It reacts with oxygen to produce CO2 and water. So when you burn methane, it also reacts with oxygen to produce CO2 and water. So the way you balance a chemical equation is you first start with the substances and you put ones in front of all of the chemical formulas. And then if you draw the Lewis structures for each substance involved and count the elements that you start with and those that you end up with, or the atoms that you have on the left and on the right, you'll see what's going on. So 1 molecule of methane and 1 molecule of oxygen, 1 molecule of CO2 and 1 molecule of water. How many carbons do we start with? On the left-hand side, there's only carbon over here, and there's only 1 atom in this molecule. So we have 1 carbon atom on the left. Hydrogens, the hydrogens are here, and there are 4 atoms of hydrogen. The oxygens are there in the O2, okay, and there are 2 oxygen atoms per molecule. Okay, on the right, we have the carbon is in the form of CO2, okay, so there's only 1 there. And then you have hydrogens in water. You have 2 hydrogens in the water molecule, so 2. And then you have 3 oxygen atoms. So you can see there's something going on here that doesn't seem right. If you have one of these molecules and one of those molecules, and you only form one of these and one of those, well, what happened to the other hydrogens? You started with 4 hydrogen atoms, and you're only left with 2, okay? So, there's a problem here. Atoms don't just go missing. You see, the law of conservation of matter says that atoms cannot be created nor destroyed in a chemical reaction. So what we do in order to fix this problem is we adjust the numbers of molecules involved. Okay? And so we need to balance the atoms that we start with on the reactant side with those that we end up with on the product side. And we have 3 different types of atoms. You see, the carbons are already balanced, but the hydrogens and oxygens are not. So we need to balance these 2. And I'll give you a clue. Since oxygen comes in the form of an elemental substance, we're going to save that one for last. You ever see any elemental substances balance those atoms last? So we're going to do the oxygen last. So let's fix the hydrogens. We have to bring this 2 up to match the 4. Okay, you always bring the lesser number up to match the higher number. Okay, and to get 4 oxygens, 4 hydrogens, we will put a 2 in front of the water. So instead of just forming 1 water molecule, let's form 2 water molecules. Okay, so now we have a 2, and let's recount all of the atoms. Okay, so on the left everything's the same because we didn't change any of the numbers on the left. We got 1 of these molecules, 1 of those molecules, so that's 1, 4, and 2. But on the right, now we have increased our atoms. So we still have 1 carbon, but now with 2 water molecules, we have 4 hydrogens. That fixes our hydrogens. And the oxygens, we also gained another one, so we got 4 oxygens on the right. Okay? So everybody's balanced now except for the oxygens. And let's bring the 2 up to match the 4 by giving ourselves 2 oxygen molecules. So by putting a coefficient 2 here now to give 2 molecules and counting everybody up, you can see that everybody is balanced. Okay, so what actually happens here, the way you interpret this balanced chemical equation is as follows. That you can either provide the molecular interpretation or, as we'll see later on, the molar interpretation. But the molecular interpretation is pretty straightforward. So you can see that 1 molecule of methane gas reacts with 2 molecules of oxygen gas to produce 1 molecule of carbon dioxide gas and 2 molecules of water vapor. So that's how you read this from left to right. So one more time, 1 molecule of methane gas reacts with 2 molecules oxygen gas to produce, with the help of a spark, if you have that written over there, 1 molecule of carbon dioxide gas and 2 molecules of water vapor. Okay, so that's how you interpret chemical equations. Let's do another example, a little more complicated. This time we're not going to draw the molecules. Another combustion reaction, so you're burning something again, and this time we'll burn octane. The formula for octane is C8H18. So octane is a liquid, and when you burn octane, you react it with oxygen gas to produce CO2 and water. And again, starting with coefficients of 1s all across, you count up all the atoms. And if you have 1 octane molecule, okay, 1 times 8, 1 molecule, 8 carbons per molecule. So 1 times 8, that's 8 carbons that you start with. Hydrogens, okay, there are 18 hydrogens per molecule. So 1 times 18 is 18 hydrogens. And then for oxygen, 1 times 2 is 2 oxygen atoms. Okay, on the right, CO2 and water. So you have 1 CO2 to start with. So 1 times 1 is 1 carbon. For the hydrogens, our hydrogens are over here. You got 2 in the water. So 1 times 2 gives you 2 hydrogens. And then for oxygens, you got oxygens here and there. So 1 times 2 is 2. Then 1 times 1 is 1. So 2 plus 1 is 3 oxygens. So you can see that nothing is balanced here. Okay, so this one's way off. So again, we're going to save oxygen for last because it appears as an elemental substance. It's easy to balance elemental substances. Now, you can balance either the carbons or hydrogens first, and let's just do the carbons like we did before. So we're going to bring the 1 up to match the 8. Okay? And you cannot change the identity of the substance. Okay. Oh, did I say we're balancing the carbons first? No, this here we're going to balance the hydrogens first. Okay. So we're going to bring the 2 up to match 18. 2 up to match 18. Okay. And now we cannot change the formula itself. To increase the number of hydrogens, we can only change the coefficient in front of the formula. So to get 18 hydrogens on the right, you're going to need 9 water molecules. 9 times 2 is 18. Okay? So 9 times 2 is 18. Here's the count so far. So nothing has changed on the left. You got 8, 18, and 2 on the left. But on the right, you still got that 1 carbon, but now you got 18 hydrogens. So hydrogens are balanced. And then you have 1 times 2, so that's 2 plus 9 times 1, 9. So 2 plus 9 is 11 oxygens on the right. Okay, so we're getting there. We got the hydrogens balanced. Let's now balance the carbons. Okay, so again, we want to bring the lower number up to match the higher number. So bring this 1 up to match 8. And we do that. So the carbons are in the form of carbon dioxide. And so to get 8 carbons on the right, it's going to be an 8 coefficient. So 8 times 1 is 8 carbons. So now let's recount everything. So nothing has changed on the left. On the right, we now have 8 carbons. So they're balanced. And then the hydrogens are still 18. And then the oxygens, you got 16 plus 9 is 25 oxygens on the right. Okay, so everybody's balanced except for the oxygen. So let's get 25 oxygens on the left. So what do you multiply by 2 to get 25? Well, 25 halves. 25 halves times 2 gets you 25. And now, recounting everybody, they're all balanced. So these coefficients, 1, 25 halves, 8, and 9, do balance the equation, but balanced chemical equations should have whole numbers. And the way to get whole numbers is to multiply all of these coefficients by 2. So times 2, you get 2, 25, 16, and 18. And this is the simplest way to balance the combustion of octane equation using whole numbers. And you can see, if you count up all of the atoms, they're still balanced. Okay, it's just take this count and multiply everybody by 2 to get that. Now, to interpret this, you can use the molecular interpretation, or as we'll see in a couple videos from now, the molar interpretation. In chemistry, we count by moles sometimes. You know, if you're a baker, you count by the dozen. In chemistry, we count by the mole. Okay, so instead of 2 molecules of octane, let's do the molar count. 2 moles of octane liquid reacts with 25 moles of oxygen gas, forming 16 moles of carbon dioxide gas and 18 moles of water vapor. So you see, that's how you interpret it. So 2 different ways to interpret molecular interpretation or molar interpretation. Now, the last topic in this lecture is classifying chemical reactions. And we're going to do this as the textbook does this by, and I like to say that this is by the element or substance arrangement method. So there are 5 categories, and every chemical reaction fits in one of these 5 categories. Okay? First, combination. Combination reactions takes 2 or more substances and combines them to form a single substance. So it might look like this. A plus B form C. So you have 2 substances and they react to form one. So they're combining together. An example would be the combustion of hydrogen. We've seen this chemical equation before. So if you take hydrogen gas and oxygen gas, they react to form water. So you got 2 substances and now you only have 1. So these 2 are combining to form water. A decomposition is the exact opposite. Here you have one substance and it splits apart into 2 or more. Okay, so it might look like A forms B plus C. And an example would be hydrogen peroxide. Liquid hydrogen peroxide breaks down, decomposes to form water and oxygen. And you've probably seen this reaction. You know, if you've ever treated a wound with hydrogen peroxide, you know, those bubbles that form, that's the oxygen gas bubbles. Okay, so it breaks down when you pour it on a wound, you know, into water and oxygen, and this supposedly helps your wounds by killing off some of the bad bacterial cells. All right, so decomposition. One substance breaks down into 2 or more substances. Another category is single replacement. And here, in single replacement, it's like 2 elements or substances kind of switch places. And they look like A plus BX form B plus AX. So you see the A's and the B's are switching places. And an example is solid iron reacts with copper 2 sulfate in aqueous solution to form solid copper and iron 2 sulfate in solution. So you see the copper and the iron are switching places. Okay, so it's a single replacement reaction. A double replacement reaction does this twice in one go, and it looks like AX plus BY form BX plus AY, and here the A's and the B's are switching places in two different substances. An example would be silver nitrate in solution reacts with sodium chloride in solution, and these form silver chloride solid, which precipitates out of solution, and sodium nitrate in solution. So you see the AX plus BY form AY plus BX. And if your chemical reaction doesn't fit into any of these categories, then we'll just list it in the other category. And those combustion reactions we saw are in the other category. So, methane combustion doesn't really fit any of those. You're not combining, decomposing, single replacement or double replacement. This is just one of the other ones. Now, this is one method to classify chemical reactions, and there are other methods as well. You can also classify them based on their chemistry. And in Chapter 9, we will talk about acid-base neutralization reactions. Okay. In this chapter, we touch on oxidation-reduction reactions. We do that in the next video. There are also precipitation reactions where solids form out of solution. Okay, so that's this one right here. This is a precipitation reaction. Okay, so this is not only a double replacement reaction, but by chemistry, we can call this a precipitation reaction. So chemical reactions can have more than one label. This one over here, this is one of the other ones, but it's also an oxidation-reduction reaction. Okay, this is also an oxidation-reduction reaction. This single replacement is, and that one is, and that one is. So oxidation-reduction reactions are seen all over the place. These four are all oxidation-reduction. That one is not. So we'll talk about redox reactions in the next video, so stay tuned for that. Aloha.